Deepak sir, we can start now.
Fine. Okay.
Deepak sir,
Yes.
are you there?
Yes, sir. Shall I start?
Yes, sir. Please.
Okay, thank you. Okay. Okay, so I once again welcome you to this session, right, on transfer learning especially. So before discussing actually transfer learning, let us discuss a few fundamental things on medical imaging and why we are not interested in traditional neural network, why we are interested in convolutional neural network. We have just now seen the difference between machine learning and deep learning based system, right? And I mean, one thing that may come to your mind that because our goal is to ultimately build an end-to-end learnable system, why can't we have neural network, right, to design the whole system, right? So I mean, what I'm trying to say here is, given a set of images, right, your task, let's say you are given again the same set of images to you, and your task is to just simply, let's say these are images, image 1, image 2, and there are n number of images which is given to us, and your task is to again classify the images into 4 different categories: category 1, category 2, category 3, category 4, maybe grade 1, grade 2, grade 3, grade 4 tumor. And can we first of all process these images with the help of traditional neural network, which is again an end-to-end learnable, E2E learnable system. Why do we need all these convolutional neural network and all? If you want, you can also make a traditional neural network. We can make it we can make it an end-to-end learnable system. Why do we need then convolutional neural network? Right. So this kind of questions that may come to your mind, why we are not preferring this. There are multiple reasons why we are not interested in designing this traditional neural network to process these images, whether it is medical image, whether it is natural image, doesn't matter. The problem here is, what we know that the input layer takes, one-dimensional data. So what you need to initially do here is you need to fast convert images which are by default 2-dimensional or 3-dimensional in nature into a one-dimensional vector, one-dimensional feature vector. So you need to fast convert these images into, which is 2D, let's say, for example, to a one-dimensional vector. Let's say, for example, I'm considering an image having size 256 cross 256. So this dimension of the feature vector is going to be, right, one, first feature, second feature, and so on up to 256 into 256 number of features. So this many number, it is like 2 to the power 16 number of features you'll be having in the input layer. The dimension of the feature vector is going to be very high. We'll see what will happen if the dimension is going to be very high. Also, there is one more property which is going to be lost, is nothing but the spatial information. Whenever you are transforming a 2-dimensional matrix into a 1-dimensional vector to process through traditional neural network, you are losing some of the neighborhood relationship which are very, very important in images. In images, which is what is important is nothing but the spatial relationships. That's the neighborhood relationship of each of the pixels. If I take your picture through a mobile camera, and right, if I show you the picture, yes, you can easily identify it's you. But if I arrange the pixels, right, in a one-dimensional vector and show you the same picture to you, you cannot even identify yourself because there is no neighborhood relationship, there is no spatial relationship. Everything has been transformed to a one-dimensional vectors. It is very difficult to identify the objects that are present in the image with the help of a one-dimensional vector. That is the major reason why we're not interested in processing the images through the traditional neural network, which takes always one-dimensional vectors in input. There is one more reason why we're not interested is the number of parameters is going to be very, very high. Here you can see in this particular neural network, we are having 3 hidden layers: hidden layer 1, hidden layer 2, hidden layer 3. Let's say, for example, there's no rules actually, no such dedicated rules available to decide the number of hidden number of neurons in a neural network, although there are thumb rules. There are particular studies that has been made over the years to identify or to decide the number of hidden neurons, but there is no such theorem available. Fine. So let's say, for example, this is 256 into 256 is nothing but 2 to the power 16 number of neurons you'll be having in the input layer, sorry. In the output layer, you'll be having 4 neurons. And let's say, for example, I'm choosing only 100 neurons in the first hidden layer. So now the question is how many parameters or how many weights and biases will be there. Let's say weights will be there. Those weights are nothing but connected to the input layer to the first hidden layer. It will be nothing but because every neuron is connected to every, you can see over here, every neuron in the hidden layer is connected to every other neurons in the preceding layer. So the number of weights is going to be 2 to the power 1600 into 100. It is a very, very large number for the first layer itself. These many number of weights are involved in the first hidden layer. So now you think about others, and those many number of weights and parameters has to be trained by your model. The model is going to be very, very complex, right? Because we have millions of the parameters, and what we know that we'll not be having millions of the images in our in medical imaging domain. So there's a possibility that your model may suffer from overfitting issue because the parameters are very high and the model is going to be very, very complex. So these are the two major reasons why we are not interested in processing these images with the help of traditional neural network. Rather, we are interested in analyzing, or you can say processing the images with the help of convolutional neural network. In the convolutional neural network, you need not to transform the image into a one-dimensional vector. That is the first point. Second point, in convolutional neural network, these many number of parameters is not going to be there. That means in convolutional neural network, every hidden neuron is connected to some portion of the input image, not all the pixels of the input image. That is how we reduce the number of parameters. Again, we'll be having something called as a pooling layers, right? That also helps in reducing the number of parameters. But every hidden neuron is not connected to every pixels or every neurons in the previous layer. So every hidden neuron corresponds to a small region, which is known as receptive field, right? It has limited receptive field, you can call it as. Fine. So that is how actually we reduce the number of parameters. We preserve the spatial informations in convolutional neural network, and that is why it is very, very popular in analyzing the images and videos. I hope it is clear. Now we can go ahead. Why we are not interested in this? So these are a couple of questions that may, comes to your mind. And there's one more point here, right? Whenever you are applying the weights, those weights are also shared. If I ask you to apply a filter or convolve a filter over the image, so for every pixel, you will apply the same filter. That is what is known as weight sharing. You're sharing the weights, right, for each of the pixels in the image. That also again helps in reducing the number of parameters in convolutional neural network, right, while processing the image. Of course, it is clear. And this is how a typical convolutional neural network looks like. I'm not going into the details of convolutional neural network and all, because I hope this part has already been covered, right? Let me just show you how it looks like and all, right? So input will be a set of images, then we'll be having some convolutional layer, followed by a ReLU layer, like in traditional, right? And convolutional neural network, there is something called as WX plus B, and there's a phi over there, right? W is nothing but the weight, B is the bias. Geometrically, it can be called as W represents the orientation of the hyperplane, because the ultimate goal is to design a hyperplane to solve the classification problem, right? I mean, the decision boundary I'm talking about, right? And B is nothing but B decides the position of the hyperplane, W decides the orientation of the hyperplane, and this phi is nothing but is a limiting function or activation function, which limits the value, right, from let's say 0 to 1, or sometimes even -1 to 1, and sometimes it is very different, right? Like sigmoid, tan sigmoid, and we have something called as nowadays ReLU and all, having a lot of advantages over sigmoid and tan sigmoid, right? The convergence is fast. Even it is, there'll be no vanishing gradient issues as well, right? Even there are certain variants of ReLU is also available, like leaky ReLU, exponential ReLU, and so many others you can go through. ReLU is recommended for convolutional neural network compared to the other types of activation functions, right, which were used earlier, like sigmoid and tan sigmoid and all. Fine. So So you can see over here, convolution, ReLU followed by pooling. So these are very common layers which you will find in all types of convolutional neural network. And these particular layers are repeated over some times in the neural network. You can see over here, this pooling is trying to downsample the images by summarizing. You can say the input, you can say the values and all, right? Even the downscaling is not, you can say the downscaling also helps in preserving the most of the important information. Here it doesn't look like the linear interpolation and all, so which I mean through which you will lose some information. It's not like that. It's something very different. And the goal is, of course, is to reduce the number of parameters. Otherwise, the number of parameters is going to be very, very high, right? So at the end, you will find some fully connected layers. You can see over here there are some fully connected layers at the end, right? And these fully connected layers are like very similar to the kind of layers which you've seen in traditional neural network, where every neuron is connected to every other neurons, right? In the preceding layer, and there will be one classification layer at the end. And in that classification layer, what kind of activation function used is softmax activation function, which gives probability values, right? And based on the probability, our highest probability values, we used to decide that whether this belong to, I mean, let's say, for example, this particular input, right, will be having probability values 0.7 here, 0. Maybe 1.5, maybe 0. Something 0.1, and then even like this, right? So based on the highest probability, the model will recommend that, or the model is going to predict that this is nothing but class because of the highest probability values, right? So we will discuss later on, I mean, the importance of the loss functions and all while discussing the segmentation models and all. We'll see how the loss function varies from classification and segmentation and all later on. But the softmax is a very important function here, activation function, which gives us the value between 0 to 1. And if you add all the probability values, you'll get, even, sigmoid also gives us value from 0 to 1. But if you add them together, you won't get the value 1. That means the total probability should be equal to 1. But the softmax is helping us, right, in getting those probability values. And if you add them together, you'll get the value 1. That means it is just saying that the probability of, right, being class 1, class 2, and so on for other classes. And the number of neurons in the output layer depends on the number of classes you are having. That is what you all know, right? And these FC layers are not recommended, right? You cannot use more number of FC layers at the end, because if you use more number of FC layers, so the number of parameters are going to be very, very high. You might have seen in case of AlexNet, right? AlexNet, there are different convolutional neural networks that have been developed over the years. The first convolutional neural network architecture, which is very popular, known as Day-8 architecture, was published in 1998. It's not at all a new concept. If you're still thinking that convolutional neural networks are new concepts, it's not like that. It all started in late 90s. Or late 80s, you can say, but finally it got published. The Day-8 architecture was published in 1998. Then from 1998 to 2012, there was no development in the field of convolutional neural network. In 2012, there was one architecture that came into the picture known as AlexNet, proposed by Professor Hinton and his group. Professor Hinton is also the developer of many algorithms, right, including the backpropagation algorithms, autoencoder. There are a lot of concepts he has proposed, capsule networks and all. And he has also recently been awarded Nobel Prize, right, in the field of physics. He has contributed a lot, right, to the field of neural networks. So backpropagation is his major contribution, and AlexNet has shown the path, right, towards developing this convolutional neural network, which everyone is using to solve real-world problems. So although Day-8 was proposed in 1998, it was not that popular, and AlexNet became very, very popular in 2012. There were no developments in between 1998 to 2012. It was AlexNet is actually the winner of a particular challenge, right? Winner of a challenge, ILSVRC, Image Net Large Scale Visual Recognition Challenge. And these is in 2010. It all started in 2010. And the winner of the 2010 and 11 was nothing but, I mean, basically the winner have used the machine learning based approach or cello architectures, right, to solve the problem, to solve the classification problem. But in 2012, AlexNet came into the picture, and AlexNet became the winner for that year. And the dataset name was ImageNet, which is the main reason why we have multiple number of convolutional neural networks. And then after 2012, you will find the real revolution of the evolution of the convolutional neural network architectures. Once AlexNet came into the picture, people have found out certain limitations of AlexNet, certain incremental work on AlexNet, and then there are a lot of architectures that have been proposed because of this particular challenge on this ImageNet dataset. ImageNet contains 1,000 number of classes, very, very important for understanding also transfer learning. Why I'm focusing on this kind of architectures, because this is going to be helpful for us to understand the transfer learning concept, right? ImageNet contains 1,000 number of classes, millions of the images, and your task is to train the model, right? I mean, your task was to just design a model, right? I mean, especially train the model on this ImageNet data set, submit the model to the organizer, and they will test your model and finally declare the right winners and all. That was the actually challenge that time. So it is a very powerful challenge, and the winner of 2012 ImageNet challenge is actually AlexNet. And then thereafter you will find a lot of architectures like VGG16, 19. There is something called as GoogleNet. VGGNet was not the winner for 2014. It is actually the runners-up, but GoogleNet was the winner. Even if it is a runners-up, it is very, very popular till date, VGGNet, because of its uniform architecture, right? You can see. And there's something called as a GoogleNet, where you will find the developers from the Google have introduced something called as an inception net, how to apply multiple filters at a time with a different filter size to extract the features at different scales. Then you will find very, very popular, the most popular architecture is known as a ResNet, that is residual network, then dense net architecture, then mobile net, then several others, efficient net. Then there is something called as ConvNext in 2022. All these, architectures have been published in the top tier computer vision conferences, A-star conferences, and all are very, very popular papers. All have been developed using ImageNet dataset. That means these models have been trained on ImageNet dataset. Now there is a question that comes to mind, right? That may come to mind that yes, why do we need GoogleNet, although we had AlexNet? All are like convolutional neural network. What are the benefits of using GoogleNet? Why people have developed GoogleNet? Right? If AlexNet was there, why people have developed GoogleNet? AlexNet, there are certain issues which I will discuss later on, right? People have focused on actually reducing the number of parameters. At the same time, people have also improved the feature learning capability of the models over the years, right? How to extract the features, or especially the complex features, from some complex scene or from the complex images, right? We'll see, I mean, how this, this ResNet and DenseNet are the two most very, very popular architectures, right? But that people have used to solve a variety of computer vision tasks, including the medical imaging task, right? People are still using this kind of architectures to solve their task, whether it is medical imaging or whether it is, whether the images are satellite images or agriculture-based images. Still, people are using this kind of architectures. We'll see how to use these kind of architectures, which are developed using ImageNet dataset, which contain natural images and contains 1,000 number of classes, right? So we'll see whether we can use these kind of data, models to solve our problem. These models have been already trained, and we don't have much amount of data to design a model from the scratch, because design a model like AlexNet or GoogleNet and run it from the scratch, it's of course a difficult task for us, because we do not have much amount of data. So if you do not have much amount of data, if you do not have computational resources, or like GPU-based machines and all, so what you can do here is you can just transfer the knowledge of these networks to your, to your task, to basically what we are trying to do here is transferring, or you can say transferring the knowledge of these kind of architectures to solve a problem, right, at your hand. We'll discuss in detail what do you mean by transfer learning and all, right? This was actually, major motivations of why actually convolutional neural network is working well, and why it has been evolved over the years. People have tried to reduce the number of parameters in AlexNet. The number of parameters were 60 million, and more than 50 million of the parameters because of the three dense layer they have used at the end. Right? There are 3 dense layers in the AlexNet you will find, and the more than 50 million parameters are only because of these 3 dense layers. So then people thought of reducing the number of parameters by removing the fully connected layers, by not using the filters having large size. So then they come up with some architectures like VGGNet, although their plan in the VGGNet was just to use 3x3 filters, not 5x5, 7x7, 9x9, 11x11. And but again they use the 3 dense layers at the end, and that is why the number of parameters in this case becomes 138 million. It's really huge number, 138 million parameters, 60 million parameters which you need to adjust. Very, very difficult, right? And then GoogleNet came into the picture with only 5 million parameters, and this GoogleNet was developed by a team of people from Google, and they become the winner for the year 2014, right? And then there's something called the residual connections, RANs connections have introduced two very powerful, concepts. You can say in convolutional neural network they have introduced, and still people are using these concepts like the residual connections and dense connections while designing convolutional neural network or while using the convolutional neural network. MobileNet was only designed to reduce, of course, to deploy all these heavyweight models on the mobile devices. I mean, MobileNet will be is having different versions, but the parameters are like below 3 million or below 2 millions, so that it can be easily deployable on the edge devices or on the mobile devices, right? So that was the motivation. I mean, why we have multiple number of convolutional neural networks, and these are like the winners of 2014, 2015, 2016, 2017, like that. And I'm not going into the details how it works and all because it has been already discussed, right? So let me show you some of the challenges which we face in medical imaging. What are the challenges we face? The most important challenge we face here is lack of large training data set. You will not be having ImageNet kind of data set to train your model, right? Because it is very difficult to acquire the image, medical image, as well as to annotate the image, because annotation is another key challenge in medical imaging. If you're dealing with this, so annotation is very, very difficult. So what we can do to deal with these kind of issues, either you can apply something called as a data augmentation approach to reduce the problem to some extent, right? The data augmentation can be done. You can think of exploring some sort of, generative models to synthesize the medical images, and those synthetic images along with the original images can be combined together to train the model. Again, annotation, it is sometimes right, it is very, very difficult to get annotations for all the images. Let's say you are having 10,000 images and you have annotations for 1,000 images. So what about then those 9,000 images? The easiest way is to just drop those 9,000 images and go ahead with these 1,000 images, but that is what we don't want. We want to also consider those 9,000 images to train the model, because the diversity is going to be really good if you're considering those 9,000 images. So you can think of just applying some semi-supervised, right? Semi-supervised kind of approach here, right? Where some of the samples are leveled and some of the samples are, these are leveled and these are unleveled. Some of the samples are leveled and some of the samples are unleveled. So how to generate pseudo levels for those 9,000 samples and how to just use them for training the model. That is what is semi-supervised learning, concepts and all. That's what you can also think of designing, or you can, that is how you can overcome, or you can address the challenges of annotation or leveling of the medical images. Handling class imbalance is also, there are other techniques, right, which are very, very important. Like people are talking about something called as few shot learning. I don't know how many of you heard about this concept, few shot learning or zero shot learning, right? So these are also the concepts which can be applied to deal with this kind of problem. Fine. So handling class imbalance. Class imbalance is always a problem in medical imaging domain, where you will be having, let's say 900 samples for a normal category, and you will be only having 100 samples or sometimes even less than that for abnormal samples. If you design the model based on this data set, so your model will be biased towards the majority class. But we don't want a biased model. We want a model that will perform well on both the classes. So this is what is the imbalance scenario and how to overcome this kind of scenarios. There are a couple of approaches you will find. Either you may go for some sort of, as I mentioned, data augmentation techniques to increase the number of abnormal samples here to make it 900 like this, or you can also go for some other kind of techniques, undersampling or oversampling techniques, as well as you can think of exploring the generative models, all right, to generate the samples of the minority class and all. Sometimes even multi-class classification becomes difficult for us because of the inter-class similarities. If you are planning to solve, let's say different or multi-class classification task, in that case, the inter-class similarities really creates problems. And there are also a couple of other issues which I will discuss in maybe in the next lecture and all. So, I mean, what are the different issues which we found? Always we're talking about image-based features. So, although image-based features are very, very important, so can we include some sort of clinical features or text-based features, or you can say clinical features, along with the, I mean, I'm talking about multimodality, right? Where these image-based features can be combined with some clinical features to take a right decision. That can be done. There are also algorithms, right, like say convolutional neural network, although which is very, very important here to capture the local information, because convolution operations, it's a local informations, but it cannot capture global informations. Right? So global informations are very, very important in some applications. So how to capture those global informations, that is also very, very important thing. And there are also certain challenges. The most important challenge in medical imaging domain is generalization, right? Now every reviewer is also asking about the generalization performance, right? So let's say you are having two data sets, and your model is really performing well on these two data sets, and you have got a lot of results. You have shown all those results, reported all the results in the paper, but now the reviewer is asking about the generalization performance of your model. That means how your model is going to perform on the on-scene data, which is collected, from different demographic regions or using some different imaging device, right? That means you want to check the performance of your model on the on-scene data. Your model has been trained on these two data sets. You want to now validate or you want to validate the generalization performance of your model. That means you want to evaluate your model on the on-scene data. That means any samples of this data is not shown by your model. So what you will do is you will simply evaluate your model, your trained model on this on-scene data, and then based on the performance, you can say whether your generalization performance or the generalizability of the model is good or bad. But it should be good, right? It should be good. And it doesn't happen most of the time, right? When we apply our model on the new data, it always fails. But what is the major reason for this, and how to improve this kind of generalization performance is the major, you can say research area in this particular, you can say domain like medical imaging and all. There is certain, you can say few emerging challenges in medical imaging. You can also get it from our paper. I think I forget to include. Yeah, this is the paper actually. This is the paper, a survey cancer detection via convolutional neural network. And this is the paper from where actually I got this figure and all, where all these challenges have been clearly mentioned, including actually the lack of explainability. Why the model is performing well. You need to increase the thrust factor of your model. The doctors are not going to accept that, the kind of results which you have reported in the form of the tables and all. Yes, it looks good that your model is performing well, it is beating all of the models, state-of-the-art models. But the thing is, how can I trust on your model, right? So that is where actually you need to mention why is your model performing well? What is the major reason behind the decision of your model? That means you need to interpret or explain your approach, whatever you have developed, right? That is what is a lack explainable AI or interpretation of your model. So you can just go through this. You can. It is very, very important, right? To discuss about the explainability and the interpretability of the models which you have developed, right? Fine. It's not about, right, the academicians who are planning to design the convolutional neural network and who has only contributed to neural network, not like that. I mean, convolutional neural network. It's of course even the industry people like Google, Microsoft, Meta, and all those who have contributed a lot to develop different types of convolutional neural network, which you might have seen. If you go through papers of ResNet, papers of GoogleNet and all, you will find the people from Google, from Meta, and from Microsoft, how they have developed the convolutional neural networks, right? So that means there are a couple of works which are going on even in industries to develop convolutional neural networks or develop deep learning based algorithms to solve a variety of tasks, including the medical imaging task. You can see over here, there's a Microsoft Hanover project who are also focusing on analyzing the medical images. Also, there is a Google's DeepMind platform. There's a huge amount of work that is also Google is also trying to do in the field of medical image analysis and all. Right? It's not about only these companies like who are really at the top, like Microsoft, Google, and all. There are also companies like you might have heard about something called as Philips. There is something called as Samsung, right? There's something called as GE Healthcare. There's something called Siemens Healthcare. So these companies are also working hard towards developing the CAD systems, or you can say the systems to analyze the medical images and even to generate the reports. And there are a lot of advancements, right, that have been done in the field of medical imaging nowadays. You will also find a lot amount of startup, not only in our country but also across the globe. Those who are only focusing on solving medical imaging tasks. Even I met few people from many startups, like many startups. Those who are only focusing on breast cancer detection through thermal imaging. That is what Nirama is doing. You can go through their profile and check that how they are developing a deep learning based algorithms to analyze, or you can say to detect the breast cancer via thermal imaging, which is a radiation-free, non-touch procedure, right? And they have also developed a low-cost solution, and they're also sending their veins, right, to many villages to screen the breast cancers, right? So really, it's an interesting task. So at the same time, you will also find a lot of such startups in our country, even in across the globe, who are focusing on solving several types of medical imaging, right? You can say medical imaging problems, right? So the different medical imaging problems, even I met few people from the companies, they are only focusing on the pre-processing part, how to remove the noise from the CT scan, how to increase the contrast of the CT scan images. There are companies that exist, which is only focusing on this kind of task, right? And it is also currently being used in some of the hospitals, right? So this kind of, there are several tasks we can assign to our students. Even students can also work on these kind of projects, and there are a lot of opportunities even in the industries, right? I've mentioned few names, and you can also identify some other names, right? The name of the companies which are focusing on this kind of task. This is just to motivate you that this work or this kind of research is not limited to academics, but it has been, right, extensively used by the industries, right? And there are a couple of papers people are publishing over the years. If you look at the publication and the number of papers that are published from 2012 to 2023, because 23 actually we have considered up to May or June 2023. So that's why you're getting less number of papers in 2023, but actual number of papers is like growing exponentially, right? So that means the number of papers that are published on cancer detection by a convolutional neural network and medical imaging, of course, right, is really growing exponentially. That means many people are actually choosing this kind of research domain because it's very sensitive and very useful for the society. So number of papers that are published using machine learning and deep learning, of course, you will find a lot of papers on deep learning as well. And also, okay, this is something very different. How many papers in between 20 to 2012 on MICAI? MICAI is a top-tier conference in the field of, is the best conference in the field of medical imaging and computer-aided diagnosis and all. We'll talk about it later on, that what is MICAI and all. But if you want to really know the advancement in the field of medical imaging, so you can go through the articles of MICAI 2025 this year, or let's say 2024, right? MICAI 2024 and 2025, and then you will find the advancement in the field of medical imaging, right? And how the people are using CNN, or whether people are using transformers and all. So this is just a report which I have collected, that how many papers on transformer, right, was published in MICAI conference for the year 2020. You can see there are no papers on transformer. I already discussed what is vision transformer. Is another deep learning architecture, very popularly used for analyzing images and videos, right? So in 2021 there are 35 papers. In 2022 there are 62 papers on vision transformers, right? So there are a lot of papers you will find on the advanced technologies in MICAI and all. Also you will find a lot of areas if you want to really explore. And most of the papers, right, in most of the papers you will find the code as well in the data set publicly available, right? It is like a mandatory kind of thing, like code and data sets are available for most of the papers. You can also go through their reviews and all, right? You can also participate in many challenges conducted by MICAI, which is very important. So like you might have heard about something called as a Brad's challenge. It is also always associated with MICI conference. This is one of the top challenge in the field of medical imaging for tumor segmentation, brain tumor segmentation and all. And there are a couple of such challenges are happening right every year associated with the MICI. If you want, you can also become the part of this MICI, and you can also take part in challenges, or you can become the winner of those challenges. Like AlexNet was the winner, and you know the importance of the AlexNet nowadays, right? Okay. So yes, here are some of the conferences through which some of the conferences. Why I'm actually giving more importance to the conferences, you'll mostly get advancements in the field of medical imaging in this kind of conferences, especially MICI and ISBI. Those are dedicated conferences for medical imaging, and these are like CBP and ICCB are top tier computer vision conferences. But you will also get few papers in CBPR, ICCB, and WACB, and these are very important things. And if you want to really go through the journals and all, here are some of the journals. IEEE transaction on medical imaging media is there. There's a JBHI, biomedical engineering, image processing, and all. There are so many others also. But you'll get mostly the papers, right? High quality papers from these journals and conferences. Here, so I mean, these are some of the suggestions. If you want, you can just go through with these conferences and these journals, and you will get to know about the more advancement in the field of medical imaging. Fine. Now let us start discussing something called as transfer learning. Why do we need transfer learning? And of course, followed by attention mechanisms, right? We'll see. And here is some sort of, you can say contents which I would like to discuss in this particular session. So I'll start with discussing limitations of working with convolutional neural network. We have also discussed a little bit, and we'll discuss in detail. And then what is our focus in this session is actually the transfer learning. We'll see how we can adapt, or how we can transfer the knowledge of ResNet to solve a problem at our hand, right? Maybe in the domain of medical imaging. We'll see. Okay, let us first discuss the limitations of working with convolutional neural network. So what we have seen that convolutional neural network demands a huge amount of parameters. We have lot of parameters, right, in convolutional neural network. And what is our task is to, of course, optimize all the parameters, all the weights and biases in convolutional neural network, which is, of course, a difficult task, right? And sometimes you also need the parameter initializations as well as hyperparameter tuning, right? Parameter initializations and hyperparameter tuning. So we have a lot of hyperparameters, something called as bed size. We have something called as an optimizer, different types of optimizer. We have learning rate, momentum. There are a lot of things which also you need to decide, right? Those are like hyperparameters. Parameters are like which are learnable, like weights and bias. If this convolutional neural network is having so many parameters, or a huge amount of parameters in terms of millions and all, and you are dealing with a very less number of samples. In case of medical imaging, we know we don't have much amount of data. So there is a possibility that the CNN can suffer from overfitting issues. I mean, in the case of, you can say in the overfitting scenario, the generalization performance is not going to be good, right? And it sometimes requires a long time to train, or even we need high amount of computational resources, right? What does it mean? So you can see over here, I've just mentioned that AlexNet is taking 60 million parameters, BGG 138 million, I already mentioned. Inception, GoogleNet is 5 million parameters, ResNet, very powerful, 25 million parameters. And if you look at the the training time it requires, AlexNet was taking 5 to 6 days of training. Can you wait for 5 to 6 days to train your model? Right? If you're not getting good result, you need to get back to your model and modify, and again retrain your model again 5 to 6 days. It's a really time-taking process, right? So on this kind of hardware, right, and VGG was taking 2 to 3 weeks. The training of VGG, right, was taking like 2 to 3 weeks time, and it was on 4 NVIDIA Titan Black GPU, right? Although the GPU capability has been increased over the years, but this was the scenario at that time in 2012 and 2013, 2 to 3 weeks to train a model. So, right, so it takes a huge amount of time to train, and huge amount of computational resources also to train this model. So it is really difficult. These are some of the practical concerns, right, which we usually face with convolutional neural network. That means if you are planning to design a model, run it from the scratch, you may take this many number of, right, or this amount of time to train the model. It's really difficult. Just trying to overcome this kind of situations. For initializations especially, right, weight initializations and all, what we are trying to do here is we are randomly choosing the weights and biases. That is what we know from the traditional neural network, that weights and biases are randomly chosen and then back propagated with the help of some optimization algorithm. That is what we know. Right. And when there are also some dedicated initialization techniques, or you can say predefined initialization techniques, weight initialization techniques we have, that is available in the literature, and that have already shown good results compared to the random initializations. So you can just go through this Glorot and He initializations. Instead of random initializations, you can just initialize the weights, the biases using this Glorot and He, and then you can compare the performance with the random initializations, right? But in the paper they have mentioned that yes, experimentally they have mentioned that yes, Glorot and He is really, Glorot He is performing well compared to the random initializations. So at the same time, if you want, you can also start with good filter rather than taking the random values as the coefficients of the filter. For performing convolution operation, you can just if you are having a domain knowledge, you can just come up with some filters like edge-based filters with certain orientations. So that may help you in extracting some important features. But again, it is purely manual and all. If you're having domain knowledge only, you can do this. But that may help you in converge, right, the model with less number of steps compared to the random one. And there are also a couple of regularization methods we have, like L1 or L2 decay. Dropout is a very powerful, concept which can be utilized as a regularization method to overcome the overfitting issues. So data augmentation, I already mentioned, can also be used for overfitting, to address the overfitting issues and all. So these kind of procedures, whatever we have discussed, right, this is very good at overcoming these overfitting issues, but still doesn't make the training faster, which is actually our plan. So what is going to be helpful is, of course, transfer learning. So before we discuss transfer learning, right, so let us also look at some of the interesting properties of the convolutional neural network, which is really important to understand the concept of transfer learning. Okay, now you see, if you see here, because we know that convolutional neural network contains multiple convolutional layers. So there are also layers initial layers, there are some middle layers, there are some later layers, or you can say high level layers. In different layers, right, extract different informations from the images. So features learned by the CNNs are hierarchical. That means we are extracting the low level features to the high level features through different layers we have in the convolutional neural network. So the initial layers, these are very important terms, right? Very, very important. These initial layers of the convolutional neural network learn some generic features, very, very important. The generic features you can see over here, like edges, blobs, edges with different orientations, right? Or color-based features, you can say. So these features are like generic features. Whatever the input may be, right? It could be medical image, it could be even different types of image, but these features are going to be very, very important and going to be generic. That means these type of features are going to help in classifying or in solving the problems related to any image, right? Because these are generic features and simple features, you can say, and this kind of features is going to be same across different types of the image. But the kind of features which you are extracting in the later layers are very, very specialized. Very, very specialized. So the features, whatever we are getting at the end, are very specific to the input domain. So that means it is data dependent, you can say. The first one is very generic, right? Whatever data may be, so these kind of features are going to work. But the last features, especially the features at the later layers, are very specific and specialized features, you can say. That means these are data dependent. If I change the this particular picture to some other picture, so these features are going to be different because it is very specific to the input data. This is very, very important. Why this is important? Because we are going to use this concept in transfer learning as well. So next is transfer learning, of course. So there are multiple ways actually to use neural network, or especially convolutional neural network. One is training from the scratch. This I'm talking about ways to use convolutional neural network. There is something called as training from scratch, right? And there is something called as transfer learning. This model is more accurate. Sorry, this strategy is more accurate, but needs huge amount of data. Training from the scratch, although accurate, but you need huge amount of data and computational resources. Transfer learning, in transfer learning, if you don't have much amount of data or much amount of computational resources, you can go for this transfer learning. We'll see. I mean, you need not to train the model from the scratch. Rather, you can start from a good point. Let's say somebody has already developed a model, which is AlexNet, right? This has been already designed on ImageNet dataset. And now you want to use this AlexNet to solve a medical image classification task. You want to again use this AlexNet via transfer learning TL to solve, let's say, medical image analysis task. But ImageNet contains natural images. This is another task. This is known as source task. This is known as target task. So there's a possibility that this source task may be similar to the target task. There's a possibility that the source task may be different from the target task. If it is similar, what is going to happen? If it is different, what is going to happen in transfer learning? So transfer learning is again of different types, right? We'll see. And this all depends. I mean, what we are exactly trying to do here is, because we know that training from this class takes a lot of time, a lot of hyperparameter tuning, parameter tuning is required. And we need even huge amount of data. And we don't want, if you don't have much amount of data, so what you can do here is, and if you want to really reduce the training time, right? So what you can do is you can opt transfer learning, right? So that is why we are interested in transfer learning. So what exactly transfer learning is? Just now we have discussed transferring the knowledge of this AlexNet to solve your target task problem, right? We'll see what is this transfer learning here and what changes you have to make in the AlexNet architecture to solve this problem. Because what we know that AlexNet was trained on something called as an ImageNet dataset consists of 1,000 classes. Let's say you are solving a problem having 5 classes. And now you want to use AlexNet to solve your 5 class classification task. But it was trained on 1,000 class classification. How to do this, right? So transfer learning, in transfer learning, sometimes we used to, right, freeze the whole network and fine tune, or you can say retrain the last layer, which is the classification layer. And sometimes we used to also fine tune few layers, or we used to fine tune the whole AlexNet layers. We'll talk about it, right? What is fine tuning and what is this last layer and all. Fine. But transfer learning is something very different from the traditional machine learning. And in traditional machine learning, what we know that if you will be having n number of tasks, we'll be having n number of tasks, so you'll be having n number of learning systems or machine learning systems, right? But transfer learning, what it says, let's say, I mean, you are having a few source tasks and your model has learned or gained some knowledge from the source task. And now you want to use this knowledge to train another system to solve a target task. That is what is actually transfer learning. You are simply, transforming the knowledge of a particular model which has been implemented on a few source tasks to another system, or to another system which is really planning to solve a target task. And this source task and target task may be similar, may be different. Goal is very simple. The goal here is to, since the pre-trained models with good results like ResNet, DenseNet we have are readily available, weights are already available, the trained weights are available, they can reduce the time spent on training. That is what is the major goal, right? Even hyperparameter tuning. And of course, they can also reduce the need for the high-end computing hardware like GPUs and all. That is what is the major goal of this transfer learning here, right? And there are multiple ways to do this. And the choice of this transfer learning strategy depends on two things. One is the dataset size, whether the dataset is large or small, and what is the similarity between the target task and the source task. That means target task and source task are similar or dissimilar. And that is how you can decide different types of strategies for transfer learning. Let us first talk about the first one. What is the first one? The transfer learning. If you are planning to use transfer learning, and let's say the data set size is small and the source and target task are similar. It's a very good thing. That means the data set is small, you are not having much amount of data, and the target and the source data sets are similar. So then what changes you have to make in the transfer learning and what you want to do? And again, let's say you want to use ResNet or any network, right? Let's say ResNet or any network or AlexNet to solve the task, right? What we know that ResNet in the initial layer gives generic features, and in the later layers it gives specific features. And the generic features are same with respect to all kind of images, and even the spatial features is going to be same if the source and the target data sets are similar, right? Let's say if the source and target data sets are similar, even the specialized features are going to be same. I should not then modify any of the features over here because the data sets are same and I don't have even much amount of data to fine tune the features or to retrain the feature extraction layers or the feature learning layers. So what I can do in this case is I can simply randomly initialize the classification layer. This layer has to be changed, the classification layer. Why? Because ResNet was designed on 1000 class classification and you are right now, let's say, solving a 5-class classification problem. So the last layer was containing 1000 neurons in case of ResNet. And now I want to use this ResNet to solve my problem, which is a 5-class classification task, but I want to use ResNet. So what I have to do, because in the ResNet, the last layer contains 1000 neurons, I have to remove this last layer and insert a new layer having 5 neurons. And now this particular layer is getting disturbed. That means the connections are getting lost, and you need to randomly initialize the weights, and you can say uh, optimize the weights and biases that are involved in the last layer. So what you need to do then, in this case, you need to simply remove the last layer and initialize or reinitialize or retrain the last layer. That is sufficient, right? If you are only reinitializing the last layer and rest others are like frozen. These layers are frozen in this case. Only you are fine tuning or learning this last layer. That is sufficient to solve the problem. But this is the case of where data set is small and the target and the source data sets are similar. That is why you need not even change the features, because the kind of feature which you have extracted using the source data set is going to be same for the target data set because they are similar, right? The parameters of the classification layer which you have just now inserted, that's what you need to do, right, is randomly initialized and trained, and the rest of the network remains frozen. I hope it is clear. There are also options in both PyTorch and TensorFlow. To implement transfer learning, very easy concept. The next strategy is data set is small, but the source and the target data sets are dissimilar, are not similar. What you will do? So what we will do in this case here is, because we know the source data set and the target data sets are not same, that means the specialized layers or the features at the specialized layers is not going to be the same, because this is specific to this layer is specific to the source task, and this layer is also specific to the target task, and both are different, means the specialized features are going to be different, but the generic features are going to be same. And the data set is small, data set is not that large, you can go back and you can fine tune all the layers, right? Because the parameters are high and we are having less number of samples. That is what data set is small is all about, right? So what we can do in this case here is, because we know that yes, the generic features are same, and what we can do is we'll insert the images to the pre-trained models, and then we'll extract the features, we'll pass these images to the generic layers of the pre-trained model like ResNet or AlexNet, and then we will collect the features and store the features in a feature vector, and then we'll process those feature vectors with the help of support vector machine or any kind of classifier like neural network and all. So this is one of the strategies which is adopted in case when data set is small, target and source data sets are dissimilar. Let's say when the data set is large, what you will do in that case? So in that case, what you can do, you can fine tune more number of layers. You can retrain more number of layers because you have more number of samples, right? So in this case, either you can fine tune few layers or you can fine tune all the layers. When I say fine tuning, that means you are randomly, you have already, you are already using the optimized weights, right? That means, let's say, for example, AlexNet. AlexNet weights, the weights of the AlexNet architecture was already available, that means optimized. And now you are using those optimized weights as a very good starting point. So instead of taking the random values, you are taking the values, right? That means your starting point is really a good one, which has shown effectiveness in many problems. May not be effective directly on the medical images, but you need to, if you can just readjust, if you can fine tune those weights according to your data, so this can be easily conversed and you'll get a better output, right? So if the data set is large, then you can just use a pre-trained network as a good initialization, which is fine-tuned on a target data set, right? Target, of course, you need to fine-tune on the target data sets. The convergence will be faster. The time required for training is going to be less. You don't even require much amount of GPU or computational resources to implement this task or to implement the transfer learning in this case. Sometimes few layers, sometimes the whole model can be even fine-tuned, right? It all depends on the kind of data you are dealing with, whether they are similar and dissimilar. And this is another view of the transfer learning, which I was discussing. This is one architecture, right, where you want to apply transfer learning. Its contents, you can see 1,000 number of neurons. You are having, let's say, C number of classes in your target task. What you will do, you will just replace this layer with a new layer having C number of neurons. And if the data set is small, source task and target task both are same. What you can do here is you can reinitialize only the last layer and train the last layer. Rest others are frozen. I mean, you are not going to change the rest of the other values of the weights and bias. Only you are going to change, or you are going to train the last layer. It will take even less amount of time, right? And then if you're dealing with a bigger data set, then you can think of either fine-tuning few layers or fine-tuning the whole layers, right? And fine-tuning the few layers, you need to be very, very careful. And while fine-tuning the whole model also, you need to be very careful. While fine-tuning, the learning rate should be kept low, right? So that while fine-tuning, the learning rate should be low, right? Why I'm saying it should be low, because if the learning rate is going to be for a higher value, so the weights is going to be drastically changed, and we don't want to drastically change the weight values. We want to simply readjust the value so that it can be adapted to our problem statement, right? So many papers on transfer learning you will find till date in the domain of medical imaging, where people have used AlexNet, VGG, ResNet, DenseNet, and other architectures, right, to adapt to the medical imaging domain, or you can say to solve a variety of tasks in medical imaging domain, right? So that is what is all about transfer learning and how to choose transfer learning. I hope implementation will be easy for you, and you can go and you can just write a code for transfer learning, which is really easy. Only you need to load the model, and you need to remove the last layer, replace the last layer, and then you need to decide that how many layers you want to train, whether it is 2, whether it is 3, or whether it is the whole model. That is what you need to mention, and then your job will be done. You can implement transfer learning, right? If you're having less amount of data, even people are using these transfer learning techniques to first extract or learn the features from the images, and then they are refining the features with the help of some other techniques. That is also people have done. And there are a lot of work on not only in the domain of medical imaging, but also in the domain of computer vision and all. where you will find the application of transfer learning. Everywhere you can use transfer learning, right? So nowadays, I can say ResNet and DenseNet, we do not have such type of much. We do not have much amount of such type of models which were trained on millions of the medical images. Yes, recently there are a couple of foundation models you can see in the literature, which was developed using millions. You can say few millions of the images, or you can say thousands of the images, right? And again, how to use those foundation models, that is where again transfer learning comes from the picture. The transfer learning can be used to transfer the knowledge of the foundation models to solve a problem at hand. I hope the transfer learning part is clear, right? Do you have any queries till this slide? Do you have any queries on transfer learning and all? If you are having any queries, you can write them in the chat box so that I can discuss. Let me check the chat box. Is there any queries? Do you have any queries on transfer learning and all? Because it's a very powerful concept. You might have also used the transfer learning concept. Yeah. Do you have any queries on transfer learning techniques and all? Yeah, next, we will start discussing something called as the attention mechanism. Very, very powerful concept. I hope I'm audible to all the participants. Yes, you are. Okay. Fine. Now let us move to the next part of our discussion today, which is attention mechanism, a very powerful concept, right? I'll discuss actually a few concepts of attention today, and I'll continue also discussing all these things because it may take long time to finish attention mechanisms and all. Again, it is going to be helpful in segmentation based models, which we'll be discussing tomorrow. But yes, we should have understanding on attention mechanisms and why it is very, very important for us. Yeah, I mean, I could see actually there is one comment in the chat box that transfer learning gives, let me check once again the comment from Basundhara, right? So can it happen that using transfer learning gives less accuracy than normal CNN? I mean, normal training you're talking about, right? I mean, normal CNN model. Oh, of course. I mean, it may happen. It may happen if you are not fine tuning the model, right? If you are not fine tuning the model properly. Using own model is always difficult, right? You can also check on the data sets, right? Using own or using our own model, it is always difficult to get better accuracy compared to transfer learning. Why I'm saying like this? Because you need at least, as I mentioned, that you need huge amount of data to train your own model. And at the same time, the training may take more amount of time. So there could be lot of parameters, there could be a lot of hyper parameters that needs tuning to design your own model. But if you are having domain expertise, you can do that. That is, of course, a more accurate approach, but not exactly a feasible approach all the time, as it always demands huge amount of data and all. So why do we are interested in transfer learning and all? Because what we have seen that yes, if most of the models are more deeper, and the depth is more, like in ResNet or DenseNet you might have seen, that helps in learning multi-level features. And yes, of course, I mean, transfer learning, it is possible that transfer learning may give also less accuracy. As I mentioned, if you will not deal with properly, if you are dealing with a small data, and if you are not, if you are, let's say, dealing with a very small data and you are fine tuning the whole model, that means what you are trying to do here is the number of parameters are really high for the models, for the pre-trained models which I have shown, let's say, and you are fine tuning all the layers and you are not having that much amount of data, right? So in that case, there is a possibility that the model may suffer from overfitting and the model may not perform well. And there's also one more possibility is that, yes, you are only fine tuning the last layer and you are not readjusting the weights of the previous layers. That may also sometimes lead to less accuracy, right? But you need to be very, very careful that how to deal with this transfer learning. If you know how to deal with, we have discussed couple of situations, and based on the situations, if you apply the transfer learning, it will give you the better performance and with less amount of training time. That is what is the major goal here, right? Even the generalization performance is going to be really high because the model has seen a diverse set of images, and that is what is very, very important, right? Generalization. So because the model has seen a different or diverse set of images in the ImageNet dataset, so there's a possibility that the generalization performance is also going to be good compared to our model. But yes, if you want, you can also design your own robust model, which can also perform well, right? It's not like that always this is true, right? Okay, I hope, I think it's clear, Dr. Vasundhara. So, okay, fine, we will move ahead. Yeah. So I was talking about something called the attention mechanism, right? Why the name is attention mechanism, and why people are preferring this integrating, why people are actually preferring or integrating these attention mechanisms into the convolutional neural network nowadays, right? I'll spend a couple of minutes today, and then we will start, tomorrow also, I'll start discussing about some of the techniques, some attention mechanism techniques and some of the applications, right? And then we'll see how these attention mechanisms can also be integrated into the segmentation models, right? So that means these attention mechanisms, then the idea was brought from the, of course, from the human vision systems, because what we know that humans can naturally and effectively find the important regions in any complex scene, right? I'll show you also one example. If I ask you something, obviously, you can also tell me the same answer, because it is natural to the human vision system that, yes, we always look at the salient regions in the complex scenes, right? And we are just trying to mimic the behavior of the human vision systems, and that is why actually attention mechanisms came into the picture, right? So we'll see what exactly. Let me show you something called as attention, and there's one picture for you in this particular slide, you can see. And the question here is, what is the boy doing, right? Ask you the question by showing you this particular image, that what is the boy doing. I hope you will be only focusing on this particular part. You will not be focusing on the other parts, because other parts are like irrelevant for our task, right? So our focus will definitely go to this part. And you can say the boy is riding a bicycle, right? That is what his attention is all about. So while the model, right, let's say your model is also generating a caption here, is the boy is riding a bicycle, whether the model is really focusing on this particular part or not. It should actually focus on this part. It should ignore the other parts simultaneously. It should not consider features from the other parts while taking the decisions. That is what you need to make sure. And this is only possible with the help of these attention mechanisms. If you integrate these attention mechanisms into the convolutional neural network and the other architectures, right? So that will make sure that, yes, my model is focusing on the right part or in the salient regions based on which it takes the decision, right? So how to integrate these attention mechanisms? What are those? How to mathematically define those attention mechanisms, right? Very, very important concepts, even for explainability and interpretability of the model, right? You can see over here, so human beings automatically identify the artifacts naturally in the image, right? And your task is to just pay attention to these relevant tasks. Other parts are not important for us at all, right? So how to just make sure that your model is focusing on this part and ignores, right, or the other parts of the image. You can take an example of a caption generator, right? That was published in ICML 2015 conference. You can see over here, when the model is trying to generate a caption, let's say here there is a woman and along with his child, and along with her child is throwing actually a frisbee, right? So you can see over here, there's a woman here, and the model is trying to generate the caption. So when the model is trying to generate the caption woman, so now you see it is focusing, the model is trying to focusing on the woman. So when the model is trying to generate something called as frisbee, so now you can see the model is trying to focus on the frisbee. So that means the kind of generation of the caption is absolutely correct. The way it is generating the caption is absolutely correct, right? Because it is somewhat focusing on, you can see over here, when the model is generating the word park here, and it is now not focusing on the woman and her child, so it is only focusing on the park side. You can see over here, right? So I mean, this is how, I mean, this is why actually this attention is very, very important for us. So attentions are of basically two types in general. It is of hard attention and soft attention. Hard attention, you need to identify a single position, and then you can apply these attentions over it. But it is not exactly all the time that you have to only decide, and selecting also one particular position is a very difficult task. Soft attention is very, very popular, where all position will be having some weights, and you need to attend all the weight, I mean attend all the positions in the image, but you need to, based on the weights you can give, based on the weights you can say, yes, this part is more important for us, or this part is not important for us, like this. So that is why soft attention is more popular nowadays, because hard attention, getting a single position is very, very difficult. Another important point or definitions of this attention is like, right. So what is our goal in case of this attention is just to improve the representation of interest. That means focusing on essential features while suppressing the unnecessary ones. That is what we discussed right now. And this attention mechanism can be considered as a dynamic selection process. We'll discuss it later on. What do you mean by this dynamic selection process, and what is basically selects, and why the name is so-called dynamic selection process? And that is realized by adaptively weighting the features according to the importance of the input. Sounds really weird, but yes, very easy to understand. Not that very difficult to understand, right? I'll discuss in detail what is this dynamic selection process and all. So what is important here is this incorporating these attention mechanisms, which is really helping us improving the representation of interest, and which can be also considered as a dynamic selection process. And what is this weighted mechanisms, and what is adaptively weighting mechanisms, and all, and how it is helping in dynamically selecting some important parts of the image, right? Or you can say some important things from the features. We'll see later on. And but incorporation of these attention mechanisms with the convolutional blocks can significantly improve the performance. You can go through the literature also, you will find that how these attention mechanisms are helping in improving the performance of the model, as well as enhancing the explainability of the model, which is very, very important. In general, the attention mechanisms can be, or visual attention, right? I'm talking about visual attention. The visual attention mechanisms are of two types. One is channel attention and one is spatial attention. Channel attention, I'll discuss in detail what exactly this channel attention is, what exactly this spatial attention is, and what is this, what this channel attention tells us what to attend. Spatial attention tells us where to attend. And you will also find a combinations of channel and spatial attention. And here is some of the attention mechanism names like squeeze and excitation. Here is something called a C-bomb, which combines both channel and spatial attention. And there is something called as a spatial attention. You will find something called a self attention, which is very, very popular in vision transformer architecture. This is one kind of attention which is used to develop vision transformer models, right? And there's also something called as temporal attention, which says when to attend. And there are also, of course, different types of attention mechanisms we have. So you can just go through this paper if you really want to know more about the visual attention mechanisms. This is a very good paper, right? Published in 2022, which gives the idea of these attention mechanisms, even what are the different types of attention mechanisms we have at 2022. And what are the challenges in this kind of attention mechanisms, right? So I mean, I will continue my discussion actually from this point, right, tomorrow. But let me before I stop, so let me show you some outputs, right? Let me show you some outputs of the, or you can say the benefits of the attention mechanisms, right? So here is, you can see a set of images, input images we have. I'll discuss the mathematical part tomorrow because it will take some time, right, to discuss and all. And you can see here are some of the input images given to us. And here is the grad cam, or you can say uh, saliency map results. So you can see the grad cam results, right? Okay, the activation map results and all of the image of this particular image by the Resonate 50 model. There's no attention involved in it. Now you can see over here. See, the output of this particular image, I mean, the class level which is predicted by the model is not this particular girl and all. So it is a crooked ball, right? So this ball is here only. The model should not focus here or here or here. The model should focus only here because the prediction is something called as a ball here. But Resonate is trying to focus here as well as focus here. Resonate with this squeeze and excitation, which is a kind of channel attention, tries to focus only on this part and ignores other parts. You see, right? Previously, with only Resonate, the model was focusing on the important region as well as on the unimportant regions. But here, the model is focusing on the important region. But CBAM is even more precise. CBAM is even more precise. Sometimes it is also focusing on the ball area as well as some of the outer regions, but it is even more precise. You can see in some other cases, there are some cases like here, you can choose the snow leopard case here. In case of slow leopard, so Resonate is having more, you can say, yeah, the heat map. These are all heat maps, right? Heat maps, or you can say grad cam maps. You can see over here. It is really focusing well on this area, right? But with channel attention, right? Again, this part particularly, but with CBAM is another kind of attention which combines both channel attention and spatial attention together, is trying to focus all the parts, right? All the important parts, right? So that is how actually the attention is going to help us in improving the performance of the model as well as improving, right, the explainability of the model. That means the model should only focus on the important part and it should ignore the other parts. There are a couple of attention mechanisms which I will discuss tomorrow, like squeeze and excitation is one of the attention mechanisms. How to implement this? What is this, right? And what is the CBAM? What is the CBAM? These are, the results we have just now seen. We got motivated from this. Yes, this is really helping us in improving the performance of the traditional convolutional neural network. And it is also trying to locate the important regions and all. And let me also show you some of the case studies, which I'll also show you tomorrow. So here is some of the attention mechanisms which we developed, right? And this is actually the whole attention mechanisms which we developed, known as channel split dual attention, right? We'll discuss tomorrow in detail. That was published in 29th International Conference on Image Processing, one of the oldest conference in the field of image processing. And this was the result which we have got. You can see over here. Here the model is focusing. Here is the tumor part. Here is the tumor part over here, but it is not that focused. It is also focusing on some other parts, which is actually not necessary here. This is not the tumor part. This is a tumor part. But so now you see, I mean, our model at least could able to. It is not that focused, but later we have developed even more, we can say efficient models, which usually focus on this particular part, right? Here also you can see the tumors. Here you can see the tumors. And it is also focusing on other parts, right? So that means this is, there are also a couple of examples which I'm having, right? You can see over here. This is basically an retinal fundus image. We have also a session on this, right? We'll discuss in detail. There's a retinal fundus image over here used to identify certain eye disease. And here is actually, there's a hemorrhage here. And if you want to really identify whether there's a hemorrhage or not, and because based on this, your model has predicted some class level, right? It's especially for diabetic retinopathy grading. And the model should only focus on this part. It should not focus on the other parts. Like other parts are like optic cup or optic disc, or let's say these are like vessels, blood vessels and all. It should only focus on the important part. You can see over here how the model with the attention is focusing only on the important part. It is not at all focusing on the other parts. And that is how actually attention is going to help us in focusing on the important regions. And that is what I mean. Let's say you are extracting the features or you are learning the features, how to focus only on the important features and ignore the other features. And it should happen actually dynamically, right? We don't want to make it fixed, so we want to make it learnable, right? And that is why we're interested in this kind of attention mechanisms. We'll discuss in detail tomorrow, and then we will discuss what are the state of the art models we have, deep learning models we have for solving the segmentation task, one of the most challenging and powerful tasks in the field of medical imaging. So I'll stop here. If you are having any queries, please write it in the chat box. I will happy to answer, right? If you're having any queries, let me stop the sharing the screen process and then, okay. Do you have any queries?
Participants, we are open for the queries. If you have, then you can ask.
I think, sir, they cannot unmute their mic, right? They can only write in the chat box.
No. They cannot unmute, but they can write their queries at chat box.
Yes. Sir, we'll wait for 2-3 minutes because they may be typing.
Yes. Meanwhile, participant, just to inform that tomorrow we have a thing from 4 o'clock, just to make up, as we have a holiday on Thursday for 2nd October. So we have a session tomorrow 4 o'clock. Okay, so we have a 4 to 8 lecture schedules tomorrow. Okay, I think, sir, if you can read out the question that S. Chandrasekhar has asked, which mechanism is best of all?
Okay. Which mechanism is best of all? May I know, are you talking about the attention mechanism or any other mechanism?
Yes, S. Chandra, if you can elaborate your question, then it would be
Which
easier
mechanism
for
is
sir
best of all?
to-
So may I know what kind of mechanism you are, okay, which mechanism? Yeah. Can you mention the mechanism? I mean, what kind of mechanism you are? Is it the attention mechanism or anything else you are talking about?
Yes, S. Chandra. Till now, what discussed?
Discussed. Okay. I mean, of course, deep learning, right? Compared to machine learning, whatever we have seen, right? Because we have seen its most important features, like you can learn the features, right? I mean, the characteristics I'm talking about. Again, when we talk about something called as, convolutional neural network, or among all the deep learning architectures we have for analyzing the images, see, convolutional neural network is, of course, the most suitable one. Again, what we are trying to do here is we are just trying to empower, or you can say you are trying to just increase the potential of the convolutional neural network, or you can say how to deal with different situations. Based on the situations, you can say this mechanism is good or this mechanism is not good, right? So if you are dealing with a less amount of data, you need to identify, yes, you need to go for, of course, transfer learning. Again, this attention mechanism is something very different, which is like a, you can say, which can be easily integrated, right? It's a plug and play module. It can be integrated into any architectures to increase the performance, right? So it is a plug and play module. If you want, you can also include with any of the architectures. That also we'll discuss later on, because even sometimes these attention mechanisms leads to some of the parameter. If you are integrating the attention mechanisms, your parameters are going to increase. So how to also deal with those kind of problems, that also we will discuss, right? So of course, I mean, when I say it's convolutional neural network, and there is again something called as vision transformer. So there are differences, right? I mean, there are also applications where CNNs are performing better. There are applications where VITs are performing better. And people are now combining CNNs and VITs together, which I will discuss tomorrow also. And that is what people are doing right now, that people have found that CNN is having some limitations. VIT is having some advantages over CNN, but VIT is also having some disadvantages that even CNN can solve. So why not to combine then CNN and VIT together, known as convolutional transformer, right? I'll talk about it. What do you mean by a convolutional transformer? It is a very, difficult questions to answer, right? Which is the best among all. No one can claim that this is the best among all. But yes, based on the situation, based on the problem statement, we can say this algorithm is better than that. The second one is like, so can we detect progressive sentiment changes in the video? Yes. Why not? Why not? I mean, you're talking about the video data and all. And if you are really want to identify the changes of all, so yes, you can do that using transformer. Of course, when I say transformer is by default attention based, right? So in transformer, you will always find self attention, right? So transformer, the major component is attention only, and that is why it is performing well, right? You can detect with the help of any algorithms, and of course with the help of transformer, attention based transformer architectures and all. You can go through the literature also. You will find a lot of papers on change detection. You can solve progressive change detection in the videos using transformer. Yeah, I think so. There are no other queries. If you are having any queries and if you want to interact with me, I am writing my email ID in the chat box. You can drop me. Oh my God, I think it's not working. So please drnaik.cac@mnit.ac.in. So that
I
is
think,
what.
sir, it is being shared with them.
Okay.
I
Then
have shared the
this is
schedule
my
over
email ID.
there.
Yes.
All the experts' email ID is there.
Oh, that's
Okay.
great then, sir.
So,
Yeah.
so means there should not be any issue with them. Okay.
Okay, sir. Thank you.
Thank you, sir, for joining with us today. Hope to see you tomorrow again. So,
Thank you.
participants, with this, we are ending up our day 8 for today. Again, I am mentioning that tomorrow we have a session starting from 4 o'clock because means we have a holiday on Thursday. To just make up that. So tomorrow we have a 4-hour class, 4 to 8. Okay. So in between we have a definitely have a break, 2-3 breaks. So no issue with that. So tomorrow again we will meet at 4 o'clock. Thank you all of you. See you tomorrow.